Welcome to PM Ready, your guide to becoming PMP certified. This lesson is on planning quality, Part 1. This lesson answers the question, what is quality? It discusses the principle of prevention over inspection. It introduces the two main categories of sampling, distinguishes between tolerances and control limits, and dives into the inputs, tools, techniques, and outputs of the plan quality management process. There's only one process in the planning process group for the quality knowledge management area, and that's the plan quality management process. As you would expect, the primary output of this process is the quality management plan. However, there's another primary output, and that's the quality metrics that will be used to measure quality on your project. Most people use the word quality when what they really mean is grade. Quality is the degree to which a set of inherent characteristics fulfills requirements. Grade, on the other hand, is a category or rank used to distinguish items that have the same functional use but do not share the same requirements for quality. For example, a car that costs $50,000 that is in every way superior to a car that costs only $20,000 is higher grade, but not necessarily of higher quality. Quality is the measure of how well something meets the requirements. If all the customer's requirements are met by the $20,000 car, then the $50,000 car is of lower quality than the $20,000 car. The more expensive car is higher grade, to be sure, but it's lower quality. A common refrain is under-promise and over-deliver. Well, that doesn't apply to project management. Projects need to deliver what is needed, no less and no more. In fact, sometimes providing a solution of higher grade than specified, even if it costs the same, is a violation of clear quality and even safety requirements. Consider the example of a house that has different electrical circuits for different rooms and areas of the house. Each of these circuits is routed through a panel of circuit breakers of various amperage. If you put a 50 amp circuit breaker on a circuit that's rated at 20 amps, you've installed a higher grade part, but created a fire hazard because the circuit breaker won't trip and stop the flow of electricity when the circuit is overloaded, and this can start a fire. When it comes to project management, we have to be more careful to distinguish between quality and grade and make sure that we deliver to specifications. Sure, if you have an idea about how to improve the quality of a deliverable, you should discuss it with the key stakeholders to make sure that it's something they want. But don't just do it thinking that you'll surprise them with higher quality. It may work out most of the time, but sometimes it'll backfire. So it's best to clear all such ideas with the stakeholders. Most people also confuse accuracy and precision. The target on the left demonstrates more accuracy, while the one on the right demonstrates more precision. When it comes to quality measurements, accuracy is how close you are to the goal. Precision, on the other hand, is how consistent the measurements are with each other. It's important to understand that just because your outputs or processes are precise, that doesn't mean that they're accurate. It's best, of course, if your processes are both accurate and precise. To specify a required level of accuracy is to specify the acceptable range, such as the range of schedule or cost estimates, like plus or minus 10%. To specify a level of precision is to specify how much you'll round numbers with several digits of precision. Or alternatively, how many digits of precision are required in your measurements. For example, when estimating a number in the hundreds of thousands, the less significant digits are usually not all that reliable. If the estimate of $198,782 has a level of accuracy of plus or minus 5%, then it doesn't make sense to report the estimate with this level of precision. It gives a false sense of accuracy to the estimate. In this case, it makes more sense to round the estimate to $200,000. On the other hand, you may specify that measurements taken need to be in inches and have at least 3 significant digits of precision, meaning that in a measurement of 5.97 inches, the digits are accurate all the way to the 7, that the 7 is definitely a 7. It's not a 6 or an 8 or anything else. You can count on that 7 being a 7. When it comes to quality, our motto is prevention over inspection. It's much better to prevent errors and defects by designing deliverables and processes that are of higher quality than it is to rely only on inspection to catch these issues before they get to the customer. It may seem like a lot of work up front, but decades of experience has shown that building quality in up front saves money overall. The cost of quality is more than the costs of building quality in. It's also the costs of poor quality. All the defects that reach your customers cost you. They cost you in product returns, warranty work, lost business, and even legal liabilities. These types of costs are known as external failure costs and are part of the cost of quality. You definitely want to minimize these costs. If you catch and fix defects after they have occurred, but before they go out to the customer, then these cost you money because you have to fix or rework the deliverable, or perhaps you even have to scrap it and start over. These costs are known as internal failure costs. Internal and external failure costs are in the category of the costs of non-conformance, and they're money lost due to failures to meet quality requirements. It's far better to prevent quality failures by figuring out how to do it right the first time. The costs of preventing defects are known as prevention costs and include training, documenting the correct processes to follow with standard operating procedures, getting the right equipment, and taking the time to do it right. You'll still want to inspect your work, but if you have a quality process, you can inspect just samples of your work rather than all of your work. These are known as appraisal costs and include inspections, testing, and in some cases, destructive testing. Destructive testing is when the test destroys the sample, such as a crash test of a car. Prevention costs and appraisal costs are in the category of the cost of conformance and represent the cost to avoid quality failures. You need to understand these different costs of quality and how they're categorized and organized. Projects will start with the costs of prevention, which are relatively low. During the project, appraisal costs will also start to be incurred. If you can avoid most of the costs of non-conformance, that is, internal failure costs of rework and scrap, then you can avoid an increase in the cost of quality toward the end of your project, as well as even higher costs of external failure costs after the project. If you're building quality in, you usually don't need to inspect 100% of your outputs. There are some cases in high-risk safety areas that you will, but most of the time, you won't. Instead, you'll be taking samples, testing and measuring these samples, and applying statistical methods and quality control tools to the data that you get about these samples in order to generate information about your processes and outputs. Two types of sampling that you should be familiar with are attribute sampling and variable sampling. Despite its name, attribute sampling isn't merely about measuring of attributes. All sampling measures attributes. No, attribute sampling is about the range of possible answers. In this case, it's a yes or no question, a pass-fail question, if you will. It's a measurement of whether the item sampled has this attribute or not, whether it conforms to this quality requirement or not, whether it passes or fails this test. Variable sampling, on the other hand, generates a range of answers along a continuous scale. Measurements of quantity, or measurements in units of time, length, volume, temperature, and so on. Examples include the number of defects per 1,000 lines of code, how many milliseconds it takes to load a web page, the diameter of a pipe, the number of gallons in a tank, or the temperature of an engine. Now we come to the distinction between tolerances and control limits on control charts. Tolerances are that range that's been specified by your stakeholders of acceptable results. This range of acceptable results or tolerances is represented in this control chart by these thick green lines. So all of these measurements in the middle, represented by these blue dots connected with blue lines, are within these green lines, which indicates that in this case, the outputs are within the specified range or within the tolerances of this process. The control limits, on the other hand, are these dashed red lines, and they're the boundaries of common variation in a statistically stable process, meaning that if a process is in statistical control, then all of the samples will appear within these red lines. Ideally, you'll design and engineer your processes so that the natural control limits of your in statistical control process are within the tolerances specified by your stakeholders. However, this isn't always the case. There are exceptions sometimes. For example, if you're pushing the envelope in, say, the manufacture of microprocessors, getting faster and smaller all the time, you may find that your manufacturing process isn't as stable as your tolerances, meaning that some of the chips you manufacture, or a certain percentage of the chips that you manufacture, will not meet specifications. And if that's the best you can do with current technology, then you simply accept the fact that there'll be a certain percentage of chips that you need to discard as not being acceptable. As you plan for quality, it's essential that you incorporate your organization's quality policies into your project's quality management plan. You'll need to get with your PMO, program, portfolio, project sponsor, other project managers, and anyone else that can direct you to these organizational quality policies, procedures, guidelines, templates, and standards. And remember that these need to be tailored to the specific deliverables and needs of your project. You should take a broad view of how you apply quality principles to your project, including watching for negative side effects caused by your efforts, such as working so hard to meet customer requirements that you overwork your project team, creating more errors and rework, losing employees as they leave your team for better working conditions, and increased risks to your project and safety impacts for your team. Also watch out for and have mechanisms in place to prevent quality processes, such as inspections, from being rushed in an effort to meet the project schedule. This will only result in undetected errors that are then discovered by the customer, increasing your warranty costs, damaging your organization's reputation, reducing market share, and impacting long-term profitability, and even, perhaps, the viability of your organization. The main two outputs of the plan quality management process are the quality management plan and the quality metrics. The quality management plan describes how applicable policies, procedures, and guidelines will be implemented to achieve the quality objectives. Quality metrics specifically describe project or product attributes and how the control quality process will verify compliance to it. Notice here how the definition of the quality management plan uses the word applicable, indicating the need for you to discover, tailor, and apply the quality policies, procedures, and guidelines that are already out there. Don't start your quality planning from scratch, or you'll miss something, and it's a lot more work. Also notice that quality metrics apply not only to the product or result of your project, but also to the project itself, including how the work is done and how the project is managed. Here's a review of what's in the quality management plan. It starts with the quality standards that will be used by the project. Quality standards can come from or be adapted from your organization and industry, including your PMO, program portfolio, project sponsor, other project managers, industry standards, and even professional organizations. It should also include the quality objectives of your project. Quality objectives can be about the deliverables, such as how long it takes to load a web page or to generate a report. Quality objectives can also be about the project activities, such as air quality or noise levels at a construction site. Or they can be about the project management processes, such as how often deliverables need rework, how quickly issues are addressed and resolved, or overall stakeholder satisfaction with the process. Or, of course, the traditional measures of delivering the agreed scope on time and on budget. Your quality management plan will also include the quality roles and responsibilities. This is important because unless someone is responsible for quality, it's probably not going to get the attention that it needs. And it's not enough to say that everyone is responsible for quality. You also need someone to be in charge of quality. Someone who's an expert, a leader, someone who can be the champion for quality, and who can guide and mentor your team members in quality principles, processes, and tools. Your quality management plan will also need to specify the project deliverables and processes subject to quality review, and the quality control and quality management activities that are planned. What tools will be used? In other words, what will be quality checked and how will it be checked? Years ago, I worked for a computer hardware manufacturer that prided itself in its extensive testing. New integrated circuit boards for peripheral devices underwent numerous tests. One was to install them into literally hundreds of computers and run continuous tests all day for weeks or even months. Another was the static charge test, which simulated someone touching the circuit board with a static shock to ensure that it the shock didn't damage it. Yet another was to attach a bag of dust to the intake vents of the computer and then run it for a few days, and later open it up and see how the additional circuit board affected the airflow through the system. If you're managing a software development project, will you be doing black box testing? At what level? Key components or individual objects? Will these tests be run manually or will they be automated? And using which automated testing tools? Will you develop the tests after the code is written or before, as in test-driven development? Will you be doing white box testing? If so, what will be your coding standards? Will you test your build scripts? How? Will you do routine checks on the completeness and integrity of your code repository? How about your servers? Will you be doing load testing? Stress testing? Performance testing? Which tools will you use? Who will be responsible for developing and running all of these tests? How will the results of these tests be reported? How will defects be handled? Do you have a formal process for continuous improvement? There are so many questions like these to be answered in order to have a good quality management plan. This is the end of part 1. PM Ready is a publication of PM Guaranteed and is based on the Project Management Institute's PMBOK guide.